Hello everyone and welcome to the Mathmatiker channel. In this video, we're going to see a proof of the Bézout theorem. In arithmetic, the Bézout theorem states that two natural numbers, a and b, are coprime, if, and only if, there are two integers, x and y, such as, ax plus by, equals 1. As a logical statement, this theorem is a logical equivalence between two propositions. The first one states that the natural numbers, a and b, are coprime, and the second proposition states that there are two integers, x and y, such as, ax plus by, equals 1. In order to prove this logical equivalence, we have to prove two implications. The first implication states that, if there are two integer numbers, x and y such that, ax plus by equals 1, then, a and b are coprime. The second implication states that, if a and b are coprime, then there are two integer numbers, x and y such that, ax plus by equals 1. Let's start with the first implication. Supposing that, there are two integers, x and y, such as, ax plus by, equals 1. We're going to prove that, a and b are coprime. If d is a common divisor of a and b, then, d divides, ax, and d divides, by. Which mean that, d divides, ax plus by. But, as we supposed, ax plus by equals 1. So, d, which is a common divisor of a and b, divides 1. Which mean that, d, is equal to 1. We therefore, have proved that, the only possible common divisor of a and b is 1. Which mean that, the greatest common divisor between a and b is 1. So a and b are coprime. And that proves the implication. Let's now move on to the second implication. The second implication states that, if a and b are coprime, then, there are two integers, x and y, such that, ax plus by, equals 1. In order to prove that, let's consider and note S, the set of all strictly positive integers which can be written as, ax plus by, such that, x and y are integer numbers. If we set the value of x equal to 1, and y equals 0, we find that, ax plus by equal, a. So, a, belongs to the set S. So this set is non-empty and bounded from below. So, according to the lower bound axioma, we can fairly say that this set admit a minimal element, which we'll note, m. Since this minimal element, m, belongs to S, there are two integers, x and y, such that, m equals ax plus by. By doing the Euclidean division of a over m, we find that a equals m multiplied by d plus r, such that d and r are natural numbers and r is strictly lower than m. When we replace m by ax plus by in this equality, we find that a equals ax plus by multiplied by d plus r. This implies that r equals a multiplied by 1 minus xd plus b multiplied by minus dy. So, r can be written as equal to x prime plus by prime, such that x prime and y prime are integer numbers. If we suppose that r, which is the rest of the Euclidean division of a over m, is strictly positive, then r would belong to the set S. And since r is strictly lower than m, as it is the rest of the Euclidean division of a over m, then this would be a contradiction with the fact that m is the minimal element of S. We therefore deduce that r is necessarily equal to 0. And this means that m divides a. By a similar reasoning we can prove that m, which is the minimal element of S, also divides b. So, m is a common divisor of a and b. Which mean that m divides the greatest common divisor between a and b. And because the greatest common divisor between a and b is equal to 1 as a and b are coprime numbers, we deduce that m divides 1. Which mean that m is equal to 1. And this proves the implication. As the two integer numbers x and y for which ax plus by equals 1 are the same integers numbers that guarantee the existence of the minimal element of S, which is m. Now we have proved both of the implications of the logical equivalence that represents the Bézout theorem. Thanks for watching the video. If you find it useful, we invite you to give it a like, and to subscribe to the channel, as well as clicking on the notification button so you'll be informed of any future publications.